Hello everyone, I welcome you all to this class. This is linear algebra class, and today we'll be solving this example 2 under this topic we introduced in our previous video, eigenvalues and eigenvectors. So in this example, they told us to find the eigenvalues and the eigenvector corresponding to the smallest eigenvalue of this 3 by 3 matrix. So find the eigenvalues of a particular square matrix. So what you are going to do is that I will give you the equation you are going to use to solve it, which we call the characteristic equation. So you will write, what you are going to do, you write determinant of a minus lambda I and equate it to 0. This is the characteristic equation you are going to use to find the eigenvalues, right? So let's solve. So this is the determinant of your matrix A. You write it down as given to you on the board here. So this is our matrix A, then minus lambda. Lambda is just a scalar, right? Just a scalar. Then your I is the identity matrix, n by n identity matrix. Your matrix A is 3 by 3, so your identity matrix must be 3 by 3. So this is our identity matrix. Determinant equated to 0. So the next thing we are going to do is to use the lambda and multiply the identity matrix, right? But first, let's write our matrix A. Then minus, let's multiply. Lambda multiplied by 1 is lambda. Lambda multiplied by 0 is 0. Lambda multiplied by 0 is 0. Lambda multiplied by 0 is 0. Lambda multiplied by 1 is lambda. Lambda multiplied by 0 is 0. Lambda multiplied by 0 is 0. Lambda multiplied by 0 is 0. Lambda multiplied by 1 is lambda. Then determinant equated to 0. So continuing, this is it. So this is determinant of, we can subtract, right? 2 minus lambda, I have 2 minus lambda. 0 minus 0 is 0. 1 minus 0 is 1. 4 minus 0 is 4. 3 minus lambda, we have 3 minus lambda. Then 8 minus 0 is 8. 0 minus 0 is 0. 0 minus 0 is 0. Then 1 minus lambda, 1 minus lambda. Determinant equated to 0. So we have a 3 by 3 matrix, right? We want to find the determinant of it. So you should know that let us follow the first row. If you follow the first row, we are going to have positive, negative, positive as a sign, right? So the first, you pick the first entry of this. Since we are following the first row, pick the first entry. That's 2 minus lambda, right? Then you now do determinant of, what you are going to do is you close the row where this first entry is appearing and the column of it. That's the first entry is appearing at row 1 and the column 1. So you close row 1, close column 1. So if you do that, what is now remaining is this 2 by 2 matrix. Then next one you are going to do is go to the second entry of row 1, and the sign is what? Negative. So negative. Then the entry there is what? 0. So negative 0, determinant of. So what you are going to do is you close the column where this 0 is appearing and the row of it. So it's appearing at the second column and row 1. So we close row 1, second column. So this will be what we have. This matrix 4, 0, 1 minus lambda as the entries of the matrix. So we can create space here. So the next one we are going to have is this third entry of the first row. Have positive sign, and we have 1 as the third entry. Then you close, it is appearing at, this one is appearing at column 3. You close column 3 and it's appearing at row 1. So if you close column 3 row 1, you have this, we have this 2 by 2 matrix left. So this is basically what we have. So this implies we can evaluate, right? You start from the first thing we wrote there, 2 minus lambda into. So how do we evaluate this 2 by 2 matrix? To evaluate this 2 by 2 matrix, you multiply the entries of the principal diagonal, right? 3 minus lambda multiplying 1 minus lambda, right? You multiply the entry, then you subtract you multiply the entries of the principal diagonal, then you subtract the product of the other diagonal. That's 0 multiplied by 8 is 0. So now for this one, we have minus, 0 multiplied by anything is 0, so we have minus 0 plus 1 multiplying. Let's do the same thing as we did in this one. This is 2 by 2 matrix. To find the determinant, multiply the entry of the principal diagonal. First multiply by 0 is 0. Subtract the product of the other diagonal. 0 multiplied by 3 minus lambda will have 0. So this is basically what we have. This implies, so these two quantities will be 0. So we have the first quantity, which is 2 minus lambda, 3 minus lambda, 1 minus lambda. So this is what we have. And this result, we're supposed to equate it to 0. And this equated to 0, right? Equated to 0. So with this, we continue solving. So these three quantities are given, the product of these three quantities are given us 0. What does it mean? It means that 2 minus lambda equals 0, or 3 minus lambda equals 0, or 1 minus lambda equals 0. These are the possibilities we can have for the product of the three quantities to give us 0. So if you solve the first one, move negative lambda to the right, we have the lambda is 2. Solve the second one, lambda will be 3. Or solve the third one, lambda will be 1. So we have gotten the eigenvalues. So the eigenvalues are 2, 3, and 1. Right? So what is the smallest eigenvalue? 1, right? So we are going to find the eigenvector corresponding to what? The smallest eigenvalue. But before we clean that, let's write our matrix A first. We are going to use it. Let me write it here. I can still get it from here. 2, 0, 1, 4, 3, 8, 0, 0, 1. So this was our matrix A. So I can now clean this. So for the eigenvector corresponding to the smallest eigenvalue, we solve. So we need to solve this equation to get that. We solve this equation, a minus lambda I multiplied by capital X equated to 0. The capital X is the eigenvector corresponding to that given lambda. Then the 0 here is the 0 matrix, right? So this implies, so let's write our matrix A. We copy our matrix A and write. This is our matrix A minus lambda. Lambda now is 1, right? Because the smallest eigenvalue is 1, right? So we are solving for the smallest eigenvalue according to the question. Question says we should compute the eigenvalues and get the eigenvector corresponding to the smallest eigenvalue. So the smallest eigenvalue here is 1. So if you put lambda for 1 here, lambda multiplied by the identity matrix I is still identity matrix. So we have identity 3 by 3 identity matrix. So this is basically what we have. So then the capital X The capital X will be a column vector. It will have entry x1, x2, x3, because your matrix A is 3 by 3. That's why it has entry x1, x2, x3. If your matrix A is 2 by 2, it will have entry x1 and x2. The zero matrix, which will still have 3 entries, 0, 0, 0, because your matrix A is 3 by 3. So we continue the solving. This implies okay, we can just subtract, right? 2 minus 1 is 1, 0 minus 0 is 0, 1 minus 0 is 1, 4 minus 0 is 4, 3 minus 1 is 2, 8 minus 0 is 8, 0 minus 0 is 0, 0 minus 0 is 0, 1 minus 0 is 0. So we'll have our multiply by the column vector, then equated to the zero matrix. So this is what we have. So the next thing we are going to do is we are going to reduce this matrix using row operation, so that we can solve this equation. So for us to solve this equation, we will reduce the matrix. Now, our matrix, let's write it down and reduce it. Let's write it down. So I will try to make the first entries of each row to be 1, if that is the first non-zero number in each row. I want it to be 1. So, but if the first non-zero number in a particular row is already 1, no problem. Now in the row 1, the first non-zero number here is 1. So we don't have issue with that. So then what is, when you have gotten that first non-zero number in a particular row, that first non-zero number is called the leading entry of that row. Then the first all the numbers below that first non-zero number in the column where the first non-zero number is located, all those numbers, you make them zeros. So the first non-zero number in row 1 is 1, is located at column 1. So the numbers below it is this 4 and 0. So 0 is already 0. So what basically the only one we have to make 0 is 4. So how do we make this 4 to be 0? So I know that since this 4 is positive, I know that negative 4 plus this positive 4 will give us 0. So basically, I will try to make this 1, this first entry in row 1, which is 1, I'll make it to be negative 4, so that I can add it to this positive 4, so that it will be 0. So how do I do that? So I'm going to do negative 4. I'll multiply the first row by negative 4 and add it to second row. So that's this thing I wrote here. Negative 4 multiplied by first row, then I'm adding the result to the second row. So with this, I will do that. Let me write my first row first. The entries of the first row, I've written it down. So let's carry the operation I've written here. Negative 4 multiplied by 1 is negative 4 plus positive 4, I have 0. Negative 4 multiplied by 0 is 0 plus 2, I have 2. Negative 4 multiplied by positive 1 is negative 4 plus 8, I have 4. Then we'll write our third row, the entries of the third row. So now we are going to continue the operation. The operation has not finished. So because I told you that I want to make the first non-zero number in each row to be 1, if that row is not 0 throughout. So if you come to row 2, the first non-zero number there is 2 now. So I want to make it to be 1. How do I make it to be 1? I'll multiply that row 2 by what? Reciprocal of 2. So that if you multiply 2 by 1 over 2, that's half. If you multiply 2 by half, you get 1. So row 2, we multiply row 2 by half. That's by the reciprocal of 2. So let's do that. 0 multiplied by half is 0, 2 multiplied by half is 1, and then 4 multiplied by half is 2. Then let's write the last row. So with this, we have reduced this matrix. So having reduced it, we can now replace this former matrix with the reduced form in this equation. So we get this. So this is what we've now got. Equated to the 0 matrix. Yeah, so this is what we now have, right? So I've replaced this former matrix with the reduced form. So the next thing we are going to do is to check whether each column has a leading entry of a row. The leading entry, which is the first non-zero number in a row, the leading entry of row 1 is 1, is located at where? Column 1. So column 1 has the leading entry of row 1. Leading entry of the second row, that's the first non-zero number in the second row, is 1. It's located at where? Column 2. So column 2 has a leading entry of row 2. The last row, they are all zeros. No non-zero number, so no leading entry. So this makes the last column, column 3, not to have a leading entry of any row. So, and x1 is for column 1, x2 is for column 2, and x3 is for what? Column 3. So those ones that have a leading entry of a row cannot be a free variable. x1 will not be a free variable, x2 will not be a free variable, then x3 will be a free variable because it corresponding to column 3, and column 3 does not have a leading entry of any row. So we are going to call it something. So let x3 be equal to alpha. We'll call it alpha. This alpha will be a real number since the entries of your matrix A are real, and we call it free variable. Free variable. So alpha will be a free variable. So x3 will be a free variable. So with this, we can now solve this equation. If you want to solve it, start from the last row and do your multiplication. So start from the last row, x1 multiplied by 0 is 0, plus x2 multiplied by 0 is 0, plus x3 multiplied by 0 is 0. So you have 0 plus 0 plus 0 equals 0. So do you get any value for x1 and x2 and x3? No. Then go to row 2 and do your multiplication. x1 multiplied by 0 is 0, x2 multiplied by 1, we have x2, plus x3 multiplied by 2, 2x3, right? Then equated to what? 0, right? We can make x2 the subject of the formula. Since we have already done our x3 to be alpha, we have already called it alpha. So let's make x2 the subject of the formula. x2 will be equal to, you move this positive 2x3 to the right, we have negative 2x3. So this will be equal to negative 2 alpha because your x3 is what? Alpha, right? Go to the first row and multiply. x1 multiplied by 1 is x1. X2 multiplied by 0 is what? 0, right? Then x3 multiplied by 1 is x3. Then equated to what? 0. So if you make x1 is subject to the formula, have x1 will be equal to, move positive x3 to the right, negative x3. So negative x3. But what is your x3? x3 is alpha. So x1 will be negative alpha, right? So with this, we have gotten the values for x1, x2, x3. So we can write our column vector having entry x1, x2, x3 to be equal to, your x1 is negative alpha, your x2 is negative 2 alpha, and your x3 is alpha, right? So this will be equal to, because alpha is any real number, so basically you choose a particular real number. Actually, any real number you choose will give you a vector, will give you a vector corresponding to this lambda equals 1. So basically, the alpha you choose will generate a vector. Any alpha you choose will generate another vector. So it's actually like a set. But we are going to choose a particular alpha. So we basically get one vector corresponding to this lambda equals 1. So let's choose alpha to be 1 for simplicity's sake. So if you choose alpha to be 1, this will be negative alpha will be negative 1, negative 2 alpha will be negative 2, and alpha will be 1. We are choosing alpha to be 1. So this is at alpha equals 1. So with this, we have solved this question.